Hello everyone, this time I'm going to show you a modification on the Excel table I've recently shown you, where I showed you how you can basically make your own gravity turn or rocket launch profile simulator in Microsoft Excel using basic numeric step-to-step simulation. And now I've done a modified version with a little bit more detail and simulating a Falcon Heavy launch, or roughly approximating it. It's not really exactly the launch profile that's going to be used. Of course, some information I just don't have. In other factors, I changed a few things to make it a bit more practical for this specific type of simulation, but it's kind of close and it sort of resembles a Falcon Heavy launch profile. And you can make the same table and play around with it, unlike with any more advanced numeric software, where I have to assume that some people don't have it. Uh, so what did I actually change? So it's still basically the same table. It does a basic step-to-step simulation. It has time steps. I reduced those to 1/20th of a second because the Falcon Heavy accelerates quite hard at liftoff, and getting anywhere near a similar launch profile with larger time steps is pretty hard. So I set those down to 1/20th. Good that I left them variable. I added Earth's rotation, which I did by simply adding a velocity to the rocket at launch, which is the Earth's rotation, and subtracting that same velocity when calculating speed and drag, but leaving it in the actual velocity, which the orbital mechanics essentially arise from by basic inertia. I then, of course, set the mass to the liftoff mass of the Falcon Heavy with the Tesla Roadster. These aren't exact values; they are slightly changed, but they are based on the Falcon Heavy. I did a few little notes on how much roughly the upper stage, the booster, the fuel, and so on weigh, so I can keep kind of track of that. I corrected the drag value for values based on the aerodynamic simulations I've run. So the amount of drag experienced by each stage is now the factor that it is divided by is now based on the aerodynamic simulations I've run. I've added some basic lifting body or lift effects, which I also based on these aerodynamic simulations, though I set them to be simply proportional to the angle of attack. And I even set a sort of induced drag addition where I used basically the AOA again and squared it so that the lifting body type lift also has a bit of induced drag simulated with it. I then went along and added the engine curve where the fuel consumption essentially is reduced over the launch as it throttles down as it gets lighter. I didn't really simulate individual stages or the landing of the stages yet. I might do that later. I also made the thrust to depend on the flow rate rather than setting them individually. I set that the thrust is the flow rate multiplied by the specific impulse, and I used, at least for the first stage, a specific impulse that is variable based, as you can see, on the pressure, which I did linearly. So the specific impulse goes, it's at sea level. At sea level, it is the specific impulse of the Merlin engine at sea level. In vacuum, it's the specific impulse of the Merlin engine in vacuum, and in between, it's just a linear line. So the specific impulse now goes up as we go higher up and the pressure reduces. Of course, when setting a lift, I could simply use the deviation here, which is also the angle of attack quite practically. The prograde, of course, also uses the speed already, the calculated speed already, so that it already takes into account the Earth's rotation, which I set in, so that the prograde is still vertically upward at the launch, even though the rocket is already going sideways. And then I added in deviation, usually starting rather gently, not suddenly putting it up to 5, but slowly increasing it and trying to imitate the Falcon Heavy launch profile, setting reasonable angles of attack at the so that the staging would occur at the known altitude and the known pitch value as we know it from SpaceX releases. And I also added in the deviation from the gravity turn later on as we approach staging. As you can see here, the deviation goes up as we approach staging. Then as we approach staging, I basically reset the mass of the rocket, along with changing the flow rate to the flow rate of just the center core engines. I also forcibly set the mass to what was left without the left and right booster. So here we see that the mass drops by the mass of the left and right booster empty and the fuel that is left for them for boost back and landing. And then I let it go down along with the flow rate again. I do pretty much the same as we go to center core separation and upper stage ignition, although here I slowly throttled it up, and of course I also changed the specific impulse. Now, since we never use that within the atmosphere, I stopped using this specific impulse value, which I calculate based on pressure, and is still the value for the first stage Merlin engine, and instead I now, after the separation, simply use this fixed value, which is the specific impulse of the upper stage Merlin engine. I also changed the factors for drag and lift during the first stage separation. As you can see, it changes from dividing by 60 to dividing by 200 because the center without the booster simply has less drag. I didn't change the drag and lift values when the center core was separated and the upper stage was ignited, because at that point they're already out of the atmosphere. I also did that run-along delta V calculation, which shows us that the Falcon Heavy, without the boost back fuel, that is basically taken out of the equation, so just the end payload has a delta V in the end of, in this case it's used up to 15,112 meters per second. That is of course setting it onto a mass transfer trajectory. You can see the speed value at the end is at roughly 13.5 kilometers per second, which is the speed of a normal mass transfer burn. And the delta V is just a little bit higher because we have gone upwards and through the atmosphere before. And in this simulation it actually needed to use up all its fuel to get there. In reality it will probably cut off its engines quite a bit earlier, because it doesn't have to go to quite that speed, because the transfer window is currently quite practical. It's basically going to the Mars orbit periapsis, so it needs less speed, so it will have a bit of more fuel left. Also, of course, in reality there will be a coast phase between the low Earth orbit insertion burn and the actual mass transfer burn, which I didn't simulate here because in that coast phase nothing really actually changes that is too interesting. I'll again slowly or quickly skip through the values and formulas that I added in so you can recreate it if you like. And if we print out diagrams on this, these are not completely all the way to the end, but almost. And here you can, of course, see the typical rocket ascent profile speed diagram going up faster and faster as the rocket gets lighter. As it burns fuel, it gets lighter, it accelerates faster and faster until stage separation, and then it goes faster, faster, faster again until the next stage separation goes faster, faster, faster again. And then it cuts off because I didn't let the diagram get that long. And of course the actual downrange altitude diagram now has this little dent here since it takes Earth's rotation into account, so the rocket is already moving sidewards at the start. So I hope you found this kind of interesting. I might upload the entire table to some file sharing site and link it to you. Uh, if you have any questions about the Falcon Heavy launch, about spaceflight, or about physics in general, I'm always open for questions or requests about videos I could make, although I'm currently again a bit busy with hyping for the Falcon Heavy launch. But as soon as I can, I'll try to get around to them. And of course, as always, thanks for watching.